This diagram shows two distinct models of movement. On the left, classical geometry dictates that a particle traveling along a curved boundary follows a smooth, continuous path. On the right, the Adelic Langlands framework creates a completely different structure. When the trajectory hits a localized grid intersection, it abruptly snaps exactly 90 degrees. The math driving this sharp turn is the Hecke hopping operator. Look at the phase element on the right side of the equation. The integral L of s, v acts as a direct topological correction to the metric, forcing the trajectory to absorb a non-commutative phase shift. Abstract arithmetic anomalies actively hijack continuous space. The mathematical correction physically converts a smooth curve into a sequence of sharp, rigid angles. This 3D diagram shows how we quantify that localized metric anomaly. We calculate the exact phase shift by integrating a secondary operation Z4 cocycle over the prism volume swept out by the geodesic path as it wraps around an arithmetic string loop. By equating the classical geometric holonomy to this computed topological phase shift, we extract the unified geodesic path equation. Notice the deficit parameter, alpha, in the denominator. When we expand it out, the local prime conductor, AP times log p, sits right inside the term. This specific fraction carves a conical singularity directly into the spatial metric. This graph shows the trajectory mapped onto a 2D plane. The topological class parameter, k, can only hold integer values modulo 4. As k cycles through 0, 1, 2, and 3, the graphed trajectory locks into discrete 90-degree or pi/2 jumps. Classical particles cannot glide freely through this modified space. The arithmetic strings force the trajectory to step strictly along a quantized grid. This diagram shows multiple concentric rings, representing nested string loops. When a trajectory approaches from the outside, the phases from each loop do not add together in a simple linear sum. The layers combine to create a hierarchical, nested metric deformation. We map this structure using a non-abelian Mink matrix. Because the matrix tracks whether a trajectory wraps an inner or an outer loop, it routes the paths asymmetrically, accumulating a precise topological tension at every intersection. Pause and consider the geometry here. If each individual loop applies its own localized deficit, how do we formulate the cumulative metric deficit experienced by a geodesic reaching the mth nested shell? The cumulative deficit is a product cascade of all the outer shell constraints. The trajectory must carry the geometric burden of every boundary it has already crossed. By stacking these loops, the system operates as a non-abelian gravitational lens. The deeper a classical shadow penetrates into the nested core, the harder the geometry bends its path. This diagram shows what happens when we zoom in on one of those boundaries at a finite scale. The solid line dissolves into a fuzzy quantum interface, a Tracy-Widom transition zone. Instead of reflecting off a hard wall, the geodesic wave packet leaks through the barrier. We map the wave packet's probability of tunneling across this edge using the stochastic Airy operator. The mathematical potential within this differential equation directly determines the width of the blur. A standard system boundary scales with a fixed exponent of -2/3, but here, multi-channeled fusion pressure warps the denominator into a new fractional exponent. The anomalous category scaling factor, theta sub c, dictates the specific fractal dimension of the interface. The quantum dimensions of the category explicitly dictate the physical thickness of the boundary wall. The topology sets the exact scale of the physical space. This final animation shows the complete trajectory shift. The geodesic breaches the fuzzy boundary and locks onto an isolated parallel track known as an outlier rail. We calculate the exact rate of this capture using the explicit transition rate equation, the classical presentation frequency multiplied by the quantum transmission coefficient. Look inside the exponent of the tunneling term to find the boundary parameter, b. When b exceeds exactly 1, the BBP transition triggers. The transmission barrier softens and the trajectory is permanently captured by the discrete track. This split-screen layout shows our 4 derived master equations. The phase deflection formula quantizes the sharp jumps. The nested braiding deficit measures the cumulative gravitational lens. The fractal scaling determines the exact thickness of the transition layer, and the capture rate defines when the trajectory locks onto the outlier rail. These equations prove that categorical boundaries compress spacetime into a fractal lens. They capture classical paths, stabilizing them permanently into discrete mathematical states.